Alright, here's a video for Math 2320 Fall 2016, and I want to take an example of a linear first order differential equation and how you use an integrating factor to solve it. So let's talk about whether this is the right form to be solved with the integrating factor. The standard form is going to look like this. Y prime plus some function of t times y equals some other function of t. So that's what you expect to see if you're going to use an integrating factor to solve it. The integrating factor is always found the same way. It will be e to the power that is the antiderivative with respect to t of this function here. Alright, now before we go any further, take note of the form that this takes. It is like that, and I also noticed that y is the dependent variable and t is the independent. So I could say, before I get too far into it, that this has some kind of solution of the form y is a function of t. Okay, well, so let's find that solution. First, the integrating factor. In this case, this function, which I call p of t here, is just 1. It's constant, actually. So my integrating factor is going to be e to the antiderivative of 1 dt, which I write 1 here just to be obvious that that's what I'm using. And that would just be e to the t. Okay, so we recognize what kind of equation it is. It's linear first order. And we found the integrating factor. So what do you do with it? Once you find the integrating factor, multiply everything on both sides of the equation by the integrating factor. We'll get e to the t y prime plus e to the t y, and that will be 5 e to the t sine 2t. So now we're looking at that. So why does introducing the integrating factor in this way work for us? You should always notice that when you find the integrating factor and multiply, this should always be the derivative with respect to t, if t is the independent variable, of y times the integrating factor. So just why not verify it? See that you've done it right. What is the derivative of this? Y is some function of t that we don't know, so I guess you'd say by the product rule, y prime times e to the t plus, what's the derivative of e to the t? It's e to the t times y. So we verified it is right. Now, say you integrate both sides. Knowing that the derivative of this is that allows us to integrate both sides fairly easily. Integrating the left with respect to t, I would get y times e to the t. And integrating the right, well, this might cause us some trouble. How are you going to do that? That's a product. This is actually a fairly common integration by parts formula. It is time consuming to do that one from scratch by integration by parts. So on our formula sheet, I did include both forms of an exponential times sine or cosine. And so we're looking at this one with constants a and b. So have a look at the formula sheet. And if I consult that formula sheet and I integrate, let's say first step, removing this 5, I'll say 5 times that antiderivative according to what the formula sheet tells me to do, and I can get this. Okay, right off the formula sheet. And, where was this 5? That's from there. Okay. And where's that 5 come from? Well, that would be 4 plus 1. All right, anyway. So the 5s are totally unnecessary at this point. Let's bring it to here. And what are we looking for ultimately is our solution, which takes that form. Can you solve for y explicitly as a function of t? And I'm only one step away from doing that. If I divide by e to the t, I'll get sine 2t minus 2 cosine 2t. And then about this, I guess I could say c, the constant, over e to the t power, but I'll go ahead, I'll say it like that. And there's your, what kind of function is this? Explicit, general. It's a general solution because I don't have information for that constant, so I leave it as a constant. So the explicit function of t, general solution. Explicit functions are typically what we find when we find a solution to a differential equation. Sometimes we will give implicit solutions, but here you go, an explicit general solution.